In the past decades, graphene, a two-dimensional atom of carbon, has witnessed a remarkable surge in interest due to its exceptional mechanical, thermal, and electrical properties. Markets stay staggering growth trajectory for the global graphene market with 19% of annual growth from 2020 until 2025, with a valuation surge from $680 billion in 2020 to $1,479 billion by 2035. But dear judges, why haven't we seen graphene everywhere? This is due to the widespread adoption of graphene facing challenges, notably high production costs, scalability limitation, and integration challenge, with the limitation of current most popular graphene validation methods as shown. However, the flash joule heating methods offer a promising alternative. Unlike the traditional approach, flash joule heating enables rapid graphene synthesis with milliseconds, fusion by the high energy input through the high capacitance capacitor system. This is not only shorter production but also allow us for precise control over the structural properties without the need for additional solvent. Here we present our innovation. Bottom-up graphene synthesis are welder-based flash joule heating as a low-cost graphene production methods. Aim for the further reducing the cost by substituting capacitor with arc welding equipment to enhance the visibility and flexibility of flash joule heating technology.
This research was conducted from April to September 2023 in the Faculty of Electrical Engineering of Brawijaya University and TS Center workshop. The process of our research starts with designing and prototyping the arc welder FGH, followed by flash graphene synthesis. After flash graphene is obtained, several tests are conducted that includes yield analysis to determine the efficiency of the FGH, FTIR analysis to determine the purity of the flash graphene, and lastly, cost analysis. The prototyping starts with designing the FGH. First iteration of the FGH was a modified version of the original FGH by swapping out the capacitor to arc welder and changing the material of the enclosure from quartz and PTFE tube to resin, reinforced fiberglass to further reduce cost. Components of the first iteration is as shown. Transitioning from electromagnetic relays to IGBTs or MOSFETs because electromagnetic relays exhibit higher delay on and off compared to the other solid-state transistors. In the initial device design, an Arduino Uno was utilized to control the IGBT gate with GT30G127 series. The IGBT GT30G127 requires a 12-volt threshold voltage to turn on fully, while the Arduino provides a maximum of 5V. To address this a step-up was used to increase the voltage. However, this setup caused damage to the IGBT, leading to continuous operation and subsequent damage to the step-up component. As a result, voltage spikes occurred, rendering the Arduino Uno inoperable. In the second iteration, MOSFET HY4008W with a gate threshold of 2V or 4V was tested as an alternative to the damaged IGBT. A Zener diode was added to regular voltage on the Arduino's digital output pin, preventing damage from the voltage spikes. Additionally, an infrared module, specifically KY022, was integrated into the device to complement its functionality, enhancing its capabilities for controlled operation. The wiring diagram for the flash joule heating device incorporated these adjustments as shown.
The prepared samples are then reacted in the arc welder FGH, and here are the results. In PET samples, plastic remnants persist due to insufficient energy from the arc welder within the 300 millisecond time frame, resulting in graphene formation primarily near the electrode. This can be addressed by pre-treating it with a 66 amp current for over 1 second to enhance the precursor material's conductivity, followed by applying a 120 amp current for 300 milliseconds. Note 40 samples post-FGH exhibit increased moisture and clumping, attributed to the material becoming hygroscopic due to the formation of porous laminated 2D structures and the creation of hydrogen bonded groups like hydroxyl, carboxyl, and also epoxy. The moisture in the FGH products indicates impurities like O and H, forming groups such as carboxyl, hydroxyl, and also epoxy, causing hygroscopic properties. Graphite, on the other hand, is not hygroscopic. PET materials yield remains high due to incomplete transformation caused by the high resistance value. Next is FTIR analysis. The distinct peak at around 1620 is in fact the characteristic of graphene that indicates C double bond C stretching bonds, crucial for identifying graphene. Graphene oxide shows a higher intensity peak at 3400 compared to norite, suggesting O single bond H stretching from hydroxyl groups. Despite expectations, FGH graphene appears darker than norite, indicating insignificance of the 3400 peak. The synthesized graphene feels more moist, but it is insoluble in water, suggesting hygroscopic but not hydrophilic properties. The significant peak influencing these properties is 1720 from carboxyl groups, indicative of C double bond O stretching bonds, aligning with previous studies and suggesting flash graphene production from arc welder based FJH.
On the results of our research. it can be concluded that 1. Arc welder FJH offers a simple and scalable way to create high-quality graphene that allows the use of readily available equipment and materials, making it a viable option for industrial applications. 2. The absence of peak at wave number 3400 and the presence of peak at wave number 1720 from the arc welder flash graphene is consistent with previous studies about flash graphene. 3. Arc welder FJH gives high yield value and a relatively high impurity due to incomplete and some precursor material. 4. Arc welder FJH is highly cost-effective by costing 93.46% lower than Chenitals FJH and 99.45% lower than CVT.